Okay, thank you very much, and thank you for everyone that's listening. I'm going to talk about agent-based modeling and for transport modeling, and I have this like grandiose title, and I'm going to, I guess, kind of let people down bit by bit. But before I explain that, an introduction. My name is Shone. I am a data scientist at Arup. Arup is a kind of roughly a built environment consultancy. And a lot of what I'm going to talk about now is going to be kind of themed around transport planning. But I'd love it if everyone kept an open mind about how we could use these techniques more broadly. And in fact, we do use these techniques more broadly, including most recently for pandemic or virus modeling. I personally am a data scientist. I come from like an engineering and economics, and then most recently from UCL CASA. And I work in a group at Arup called the City Modeling Lab, and we're a research kind of organization within Arup, and our big thing at the moment and for the last 2 years has been building really, really massive scale agent-based models. And I've just pulled out some kind of pretty pictures to give an idea of like the kind of the level of fidelity and also then and the scale. Okay, so of these models. I got a lot of slides to get through, and I wanted to get like a lot of content across. I'm not going to explain precisely how to build a massive agent-based transport model for planning the future. I'm going to bring out like 3 kind of key challenges that really like use spatial data, and I'm going to present these as like interesting problems to try and like sort of make people see this as a spatial data problem. But also I'm going to like hopefully present them as I'm going to present some of our solutions and what we've done. But also, yeah, these are like kind of open-ended problems, and this is very much a talk about like the direction of travel, I think, for the work we are doing. And yeah, so before I get into that, I am going to cover the context, and that's going to be what is transport modeling, and then what's an ABM, and then hopefully as I make my way through some of the slightly more technical stuff, I hope it will all fit together. The reason I wanted to present this work is because I think it is, it's like for our industry, for the built environment, and especially for transport, like it's an area of massive change where kind of recent advances in data and compute are, kind of like implementing big technical changes for the better, hopefully. So why do we do transport modeling? Effectively, so there's 3 broad scenarios where we might want to do or build a big transport model or a model. And this is because we are planning or want to fund or procure some big project or some small project, perhaps, for example, a high-speed railway link. And we're looking at what the viable options are and perhaps what the route should be. And we want to test. We want to test our project without actually obviously having to build it. And then second, we can kind of think of it as more of a detailed question. So maybe we've already decided to build a scheme, and we want to kind of decide precisely how it's going to work or how it's going to be designed. And so perhaps that might be if we were thinking about London, I live in London, we have the congestion charge zone. And perhaps we're kind of thinking about how much we should charge for certain types of vehicles, as an example. And then finally, the way we operate and manage existing infrastructure. Like we want to kind of test some of the changes we might make without actually making them. And typically, we're chasing some objective, like some organization, a government or a local organization is chasing some objective. So, this is kind of like the abstract. This is my abstract diagram of what a transport model is, and the kind of let's call it the transport model. The black box machine in the middle is taking 2 types of inputs. We're taking like inputs about the environment. and then taking inputs about people that are operating in this environment. And so you could think of the environment as maybe a road network, perhaps, and agents, obviously, in this case, as people, households full of people, or maybe simply like people in cars or cars. And then we churn this through our transport model, and out comes our outputs from our model. And these would be like, we might be looking at the choices or the actions of the agents within this environment. And then from these, we would look at emerging patterns. So yeah, like to put that in some more kind of real world context, that might be looking at where there's congestion, or looking at how long it took someone to get to work, or deciding like a very popular one, at least historically, has been kind of what is the gain in time been? So like we've improved something maybe in our model, and we've sped up people's journeys and they're saving time. What is the value of all this accumulated time saving? But the point I wanted to make was that kind of these transport models have been around for a long time, and they are very much a product of both the data and compute or techniques available at the time, and also the questions that people were asking and the problems that we had. So when we were really into cars and road networks, it was kind of the question often was like, well, how can I get people around on this network as fast as possible? Maybe where should I widen my roads? But now the question is very different. And a lot of these old kind of transport models and techniques are slightly kind of like stressed because we're asking new questions and we want new outputs. And so trivially, this might be we're more interested about emissions, but we're super interested, particularly in urban areas, about how we can perhaps get people into other modes of transport, so cycling, walking. But increasingly, this is an even more complicated question because maybe we also have some like private cycling, but maybe we have like dockless bicycles or docked bikes. Maybe we care more about journeys where people are taking several different modes of transport to achieve like some trip. And we have companies like Uber coming in. And so like the kind of the problem or the environment, if you like, is far more complex. But also the question or the outcomes that we want from the world are somewhat changing as well. And people are increasingly more interested in kind of considering the heterogeneity of people. So it's not enough to say that everyone is kind of like driving a car. Like maybe some drivers of cars are more important than others. Some journeys are more important than others, and some people are restricted in certain ways. So, for example, we can't like realistically move everyone out of private transport onto public transport. Maybe perhaps because they have accessibility issues, or perhaps they're a workman and they need to carry a lot of tools. And so this is kind of like what is required now from the state of the art. So pivoting kind of hard into what is an ABM or an agent-based model. So it's kind of like a framework or a paradigm. Like agent-based modeling, essentially, it's like a way of thinking of modeling things where you break it down into the actions of individual agents. And these agents are like modeled as autonomous decision makers, and they interact with each other and in some environment. And these are the kind of the two components which should look kind of similar to the components I showed earlier, so environment and agents. And then on the left, I have like it's like simplified kind of version of an ABM from the 1970s called a cellular automata. And I think it's basically something like nice thing to Wikipedia, like the game of life. It's a nice introduction to how these things kind of work. And it shouldn't be, I hope, too much of a stretch to think, well, actually, this is how I should probably be modeling people moving around an environment. For example, if I was interested in how they were going to behave on a transport network or in a transport network in a city. And this is not like too big a leap. Maybe like, I hope this is sort of like a sensible way to think of the world from like this agent-based level. But it hasn't like been the case because it's data-wise, it's tricky. Computationally, it's horrendous or has been horrendous. And so what I'm sort of showing you now is kind of a newer way of thinking of these problems. And yeah, crucially, this agent-based approach allows us to consider people as individuals. So just to correctly consider like true heterogeneity. And that might be in our behaviors, or how we're like restricted, perhaps if we are, for example, disabled or carrying heavy shopping, or just have different like goals or different priorities. Like this is achievable within an agent-based modeling framework. That is my hyper kind of complex diagram to try and represent this on one slide. So in the top left is kind of like let's call it the old world, the old homogeneous model world, where rather than representing individuals, we represent kind of humanity as these blocks of people. So we say like there is a flow of people from this zone A to this zone B, of a certain amount. That's in red in the top left. And then the direction that we're kind of moving in, pushing in, is the bottom right. And there's two axes of movement. There's the agents and there's the environment. So along the top, instead of having these homogeneous blobs of humanity, we're moving into individuals. And these individuals can have unique attributes, unique restrictions, and so on. And so we get like better, more representative outputs from our models, and we can ask questions about the fairness or the distributions of outcomes. And then down the vertical axis, we're moving away from this kind of simplified grid or zonal representation of the world into these super detailed networks. And in fact, what I will be showing you is networks that are so networks for cars and buses and bikes and people to walk on, but also real transit services, so scheduled vehicles moving around the network realistically. Okay, so onto the slightly more technical content. I'm not, so starting off in our kind of our environment kind of theme. The question is, how can we have the best environment in our massive ABM as possible? Where environment in this case is kind of like the road networks and transit networks and schedules. And a sub question of this, a difficult question is, like, let's say, and we do this, we scrape maybe the OpenStreetMap networks for the UK. And then separately, we get some representation of scheduled transit services, maybe for buses, from, say, GTFS or some other provider, and we want to join these together. So we want, in this case, our buses, as they move from stop to stop, to be traveling along our OpenStreetMap network. And this is a representation of this problem that other people, other groups, and also my colleagues work on. And in the top left, you have the network underneath in gray, and you have the scheduled service as a sequence of red dots. And the question is, like, as you snap those red dots, those bus stops in this case, onto sections of the network, like, how is the bus traveling between them? And this is suggesting that the correct solution is in the top right, which obviously isn't necessarily a trivial solution. And this is, we represent this as like both a spatial problem, so like quite a simple sort of snapping to close, like, nearby nodes or links, and also as a graph problem, because depending on those snaps, we get different routes the bus takes through the network. And so this is an interesting problem where we generally will have some, for each bus stop, we take a bunch of candidates, and then for each candidate, we consider the graph and the distance through that graph that the bus would then travel, and then select based on some target, typically shortest routed distance as possible. And we do this for countries at a national scale, and this is computationally horrendous. And so actually, we do a lot of work in trying to like set this problem up in a nice way. And there's two kind of tricks that we use at the moment. One is to use Google's S2 geometry, and there's a little link in the bottom left. And this sets up I guess people are somewhat familiar with it, but sets us up with an indexing system for the world. It certainly works at like the national scale. as a space filling curve, and it makes us think very quick, kind of like indexing or some spatial operations for points super quickly. And we go a little bit further and we take another step where we create a graph or a tree in this case with levels based on that space filling curve. And so this basically allows us, we choose rather arbitrarily, or we configure, like we split our space filling curves into these massive blocks. And within each block, we have this kind of, it contains the links for a part of the network. And this lets us do like really fast indexing of links of networks to points, and also creates like a natural level at which to split everything into parallel computation. So I haven't explained this very well, I appreciate, but we take the S2 geometry and we pick like an upper level and a lower level. And in that lower level, effectively each grid like contains an edge of our road network, say. And then at the larger level, all these links belong. All these links belong to some grid in this larger level. And then we can just, so we have a huge network. We produce this tree, and then we spin up maybe hundreds of computers, and we just send away the problems accordingly to each different computer. And so we can kind of process these networks super fast. Should probably answer questions about that later, where I haven't explained it very well. So yeah, we get these big networks. So this is a little extract from London, but as I keep saying, like we go for precision and then also massive scale. And we have these scheduled services moving around realistically on these road networks. The question is then was like, how well do we know our algorithm is working? The whole point is that we don't want to interrogate these things service by service. We don't want to look at the schedule for bus number 7 and check that it's in the right place, because we have tens of thousands of these bus services. And the way we've kind of tackled this problem is to build dummy or fake cities. And we have a project that's open source sitting on GitHub somewhere. It's called City Chef, where we generate these fake cities with their fake road networks and fake services. And then we basically apply a bunch of jitter or noise to them, and then produce OSM formatted output network and a GTFS formatted scheduled service, and then we can do like this massive testing and in fact calibration of our hyperparameters. And this is how we kind of like try to move to a place where we have some confidence in this process. Yeah, and the reason why I say calibration is because so if we do like a very greedy snapping of locations, then we simplify our graph a lot. Whereas if we consider a lot of nearby locations, then our graph becomes huge. And I don't know the complexity of the problem, but it gets very, very big, very, very quickly. And so kind of correctly choosing the greediness of the algorithm has a very big impact on the quality, but also the speed of the output. Okay, so moving somewhat rapidly on. And so I present this as still an open-ended problem. And a big one. So second component was were the agents, and we call this process population synthesis. And this is essentially trying to create like realistic representative people living in realistic representative households who are trying to fulfill realistic representative kind of days within our model. So we want to be able to simulate them going to work, nipping to the shops for lunch, going home via the gym. And this process, population synthesis, is all about grabbing that data. So this is a typical kind of input to the stage in the process I'm going to talk about. This is a very small population with just 3 people in, and they have what we call an activity plan for, like in this case, let's say across 24 hours. So they generally start off at home, and then there's some trip, to, in this case, typically a work activity, and then another trip to another activity, then maybe back to work or to another activity, and then home again at the end of the day. And we get this information from a variety of sources, but a nice, easy one to think of is travel diary data, which is like commonly available from national transport authorities, although of varying levels of quality. And for each of these activities, so there's home activities or work activities or shopping activities or health activities and so on. The challenge that I present here is like, well, maybe we're told from the survey that the home location is in this zone and the work location is in a second zone. Perhaps like a LSOA is a typical kind of unit for the UK. We actually, for our simulation, we need to assign these activities, this home location, to a real household, ideally. And the work location, we want to assign it to a real, say, office building, perhaps. And so that's the problem we tackle. And the question is, where do we get our, where do we get these activity locations, which we refer to as facilities? And again, we use OpenStreetMap. And so I've got 3 examples here of facilities maybe extracted from OpenStreetMap. So home activity facilities, work activity facilities, and education activity facilities. So that's kind of all very well. Like if you think, well, I'll just scrape OpenStreetMap, I'll just grab a bunch of building locations. But the problem is, typically what we've experienced with OpenStreetMap is that we have a lot of buildings and it looks great, particularly in urban areas, but we don't necessarily know what that building is used for or what it is. And so we built some tooling that kind of, it looks for supplementary information from OpenStreetMap. So like 2 trivial cases are like we search for the building tag, and then in order to assign that building some potential activities, we might look at the land use in that area, also according to OpenStreetMap, but also look for other tags within or close to that building. Perhaps if there's a shop or a post office, for example. And through this operation, we build these kind of facility maps for cities or for countries. So kind of quick recap. We started off in the top left, and then we grabbed a bunch of facilities from OSM and we categorized them as being for home or for work, for education, for shopping, for health. And then we randomly assign, or we do some form of assignment of these locations. So we say, okay, person A, they live in zone A. So we look for a home activity in zone A and we'd sample that. And this allows us then to build like this spatial representation of this kind of demand for travel, which is shown on the right. And we do, again, this like at scale. We don't often operate at like 100% samples of countries, but we operate in the kind of millions of people. So these are, somewhat big data, large data. And the way we do the sampling of these locations is important. So I'm going to show examples of 2 cases. On the left, random sampling. On the right, this facility sampling that I've just explained. And you can see, like, nationally, this makes a big difference. Like, randomly sampling locations within these zones is very different to like sampling these detailed facilities. And then as we kind of zoom in, you can see a city scale. And then probably the most useful way to think of it is this, again, is the same area shown, left on random sample, right facility sample, makes a big difference. I mean, trivially on the left, we have people living in a river and kind of walking across swampland in order to get to bus stops. And I'm having to rush. This is like an abstract way of thinking of the problem. We hope we're along the top. We hope that we're sampling like a kind of finite, limited amount of facilities within each zone. But in practice, work is needed. We often, especially in rural areas or for common facilities, are sampling more like along the bottom row. And there's a lot more variety in how that, like the sampling creates a lot of random variation. Super quickly. The third and final case is, well, I've run my simulation. Maybe I ran it for like last year, and I'm seeing people's choices and the emerging patterns, and I want to calibrate my model. I want to know how good it is. We can do like lots of macro comparisons. So we take some observed data, in this case maybe vehicle counts, for cars perhaps passing under, say, gantries on the motorway and being counted throughout the day, and we can compare it to our models, like a macro validation. It's kind of pretty old school and easy. But the exciting thing we do is this sort of mystery shopper idea, where we actually take GPS traces from real people, and we take the attributes of these people and we drop them into the simulation, and then we see how they behave in simulation. And then we can compare the choices they make, the routes they take, which bus they use, when they leave the house, for example. We could compare what we know to be observed from their real behavior to what happens in simulation. And we like to quantify these things. This is my colleague's work, as much of the stuff I've shown is. But this is a trace. So in red is what was simulated from the ABM, and in black is kind of the real trace of where they moved. And the flat axes along the bottom are that long, and then time is shown vertically. And we're kind of interested in how closely these two, let's call them traces, align, and the way we currently quantify this is by taking the convex hull of the whole thing. And it's just kind of like food for thought. Like, this is a bit of still an outstanding question for us, because this hull has a really awkward sort of unit. It's like, how can we quantify this difference better? Okay. I think I am, running out of time. So what I hope was that would be like a technical introduction to sort of the role of spatial data in the work we're doing, for building better transport models. And also hope a couple of listeners will come away with an idea of what transport modeling is, what it can be used for, and how it's getting better, and the role of agent-based models. Thanks for listening. There's 2 links here. One is to our, we sort of started publishing stuff on Medium, and we also do increasingly release projects open source. And the one here, Pam, is a live open source project in development, if anyone is interested.
Awesome. Thank you very much, Fred. I think we've got time for a couple of questions, if that's okay with you.
Sure.
Thanks for sharing all this insight. It's been fascinating. We have a question here from Caroline Broughton, who asks the question: how do you deal with topological inaccuracies in OSN networks?
So I think we don't, like, broadly speaking, and beyond topological stuff, like a massive area of concern is the difference in quality between different, say, an urban area and a rural area, and this is a massive source of potential bias in our model. Having said that, so we try to kind of have sensible, heuristics when we're going through sampling. Having said that, so there's known problems and known biases, but it's still, we'd argue an improvement over existing. And we're kind of happy that we hope we know where most of the problems are.
Absolutely. And following on from that, Trey Lanassa has asked the question: if you're using survey data for the activity plan synthesis? This is a personal belief that is not necessarily reflected by everyone that works in this domain, but I personally like very much to use. So it's kind of awkward, I guess, because it's very sensitive data, but we like to use travel diaries, so surveyed diaries of people. And my rationale behind this is because I've talked a bit about heterogeneity, like accurately representing true people's behavior, and that level of detail, like these weird little trips we make in the day, that comes from diary data. Other sources, so like more modeling heavy sources, maybe from mobile phone tower pings, for example, they're kind of like, they sound nice, but often they're particularly emitting missing short walking trips, or certain types of trips that we actually do perhaps care about for certain types of people as well. Mm-hmm.
So there's trade-offs, as I guess you can imagine, but we do use other sources as well. Yeah,
there's always trade-offs. The next question we have here from Richard Pelgrim, and he asks: how do you deal with multi-use buildings with, for example, functions split between ground level shops and work and upper level apartments and home?
Yeah, it's a good question, and that I guess is probably one of the sort of, so the methodology for scraping stuff from OSM at the moment is somewhat naive to that. And one of the things it is very naive to, for example, is like the capacity of the building. So yeah, so a simpler or trivial example would be, say, like two different schools. One of them has a single classroom for 10 pupils, and the other, a few thousand. And how do we not oversample from one of those schools? And the process, the simple process at the moment is based on area. But yeah, you've immediately identified the problem, which is urban areas with multiple floors. And I guess that tag often or sometimes exists in OSM, but maybe not reliably enough. But yeah, I guess that falls into the known problem set. So it's a good question.
Absolutely. Well, there are plenty more good questions actually on the chat. Unfortunately, we don't have time to go into all of them. But I would encourage everybody to chat with Fred directly on the platform. Mary, my colleague, has shared the links that Fred mentioned on the chat. Fred, thank you so much for joining us and for preparing this presentation. We're going to flip across now to the other speakers. Hope to see you soon.
Thank you very much.
So now